I'd like to now introduce Dr. Nigam Shah. Nigam, professor at Stanford, chief data scientist of Stanford Medicine, longtime friend and attendee of machine learning for healthcare. Nigam's lab focuses on bringing AI into clinical use safely and ethically and cost effectively. And yeah, we're glad to have him with us. So thanks, Nigam.
Can y'all hear me okay? I will tend to wander around. I'm presenting from my iPad. I like intermingling. How many of you are in the audience who know this conference as MUCMed? 2, 3, 4, yeah, a small percentage. I love that name, by the way. MLHC is kind of boring, like MUCMed, you know, it's like you're mucking around with stuff. It was MDs mucking around with computers, I think, but no, it was meaningful use of computers by MDs. Anyway, jokes. What? So what I'm going to try and do today is walk you through some of our thinking on how do we adopt AI, machine learning, or more simply, a data plus an algorithm construct in healthcare. I'm going to underline healthcare because healthcare is not the same as medicine. And I don't have to finish the slides. The slides are more of a prop. I could do this talk without any slides, and it might actually be more fun. So that's the goal. And let's get started. So I live a pretty schizophrenic life. Half of my time is spent as a faculty member doing research, teaching students, helping our, this is a little bit loud, yeah. Helping our institution figure out our strategy for research data warehousing and so on. And then I did that for about 10 years and got bored. And so then I started this new role where in the health system, I lead a team whose job it is to bring algorithms into routine use. And one of the team members, Aditya Sharma, is here. And we need to build the delivery science. How are we going to do this on a sustainable, scalable basis? A lot of talking, otherwise known as cross-functional leadership. That's just a fancy word for talking. And then getting shipped out as a prop when Stanford Medicine needs to talk about, you know, how are we doing awesome. This is not being like recorded or anything, right? So it leads to a very interesting tension. Here, it's all about writing papers. And here, mortality and money are the only two things that matter. They're the only two real outcomes. Everything else is some composition of that. Did you save money? Did you save lives? Ideally, both. You can get away with one, but you do neither of them, you're toast. And in the previous presentation, we saw nice examples of how you can toast yourself in different ways. All right, so I'll acknowledge the team up front, and I say teams because this is the lab. You might recognize Jenna Vians there. She did a sabbatical with us, so that's where the picture is from. And this is the data science team in the health system. And the reason I put this up is the size is important. Academic teams are small. Operational teams, 5 times, 4 times as big. And that scale difference is also something to keep in mind. If you're a PhD student developing a model, model's the easy part. Are you going to carry a pager once you deploy it? If not, like, you know, think through it, because if the model misbehaves at 2 a.m., you are going to get a call. All right, so that's just the setup, you know, getting sort of into the mindset. I'm not going to give you specific examples of projects we have done. I'm happy to talk about them during the panel. But what I want to do is share a frame of mind. And this is perhaps the most important side. And I am actually going to walk off stage and perhaps even go here. When someone says data, I want you to think of what's on slide here. I want you to think of a timeline. Don't think of a document. Don't think of a image, a waveform, or a data set. Patient, yeah, I should stay away from this thing. Patient experience unfolds over time. Anytime something important in medicine happens, when you go to a doctor, they say, when did it begin? What happened before that? When did it start? When did it end? Start and end. You always need to know these two things. We talk about labels in machine learning, and I'm sure a lot of you might have built labels for sepsis, for example. Well, sepsis has a start and an end. How many of your sepsis labels have an end? 0. Pneumonia starts and ends. You got to think about intervals. So this is real life, events happening. Here are different data streams. You can imagine 50, maybe 60 different tracks of information, maybe even 100. And we saw in Marina Zitnik's talk about data types that are not routine in healthcare, like proteomics. Genomics is getting there. You might have metabolomics. The standard ones are, well, in this case, just identifiers. You might have ICD and CPT codes and so on. You might have vital signs, medications, progress notes, orders. You might have heart rate measurements. Somebody somewhere took a picture. Every opening in the body, we can send a camera up and take a picture or a video, usually deleted in a couple hours, actually. And everything has a start and end. Let's call this thing the patient timeline object. You never materialize it. So if you materialize it, most of it will be blank. Two things remain true about this construct. Any given track of information, let's say ECG, there is nobody who has a complete longitudinal record over, say, 5 years. Nobody, not even the patient. And then at a given point in time, there is nobody who has all the modalities, because that's not how healthcare works. We take an X-ray when it's necessary. Like, you don't show up to your annual visit and they take an X-ray and an MRI and a CT scan and colonoscopy and everything. We just don't do that. So this thing is very sparse. And we take this thing and then we slap it into a flat matrix and then do some math on it. With me so far? So here's that, math. I'm not going to talk about deep neural nets and logistic regressions and so on. And these days, it's kind of comical that anything from a 4-variable logistic regression to a 450 billion parameter model is AI. The good news is a very broad range, very inclusive. Bad news is like anything goes. So we'll leave that aside. But I would say that we use these models to do two things and two things only. Or, well, it's 3 things, but I'll start with 2. To make 2 decisions, whether to treat and how to treat. Those are the only 2 things we try to decide in medicine. Or medicine, and then we'll get to healthcare in a second. When you go and talk with a physician, a nurse, a pharmacist, or what have you, the first thing is, do I need to do anything? That's whether to treat. Whether to treat could be a classification problem or a prediction problem. Classification is what the person already has, diagnosis. This X-ray has pneumonia. That's classification. Never ever say that I predict there's pneumonia. Nobody predicts pneumonia. Nobody predicts sepsis. You classify sepsis. You can predict deterioration, as we just saw. Prediction is hard, especially about the future. That was a joke, like I caught nothing. It's a famous joke, anyway. We can do classification, we can do prediction, and then the harder one is, let's say we figured out, yes, we need to do something. How do we treat? requires causal inference. Requires statistics, unfortunately. You can't wiggle your way out of it. No amount of deep neural nets can guarantee causal inference integrity. You will have to learn stats, epidemiology, and things like that, and deal with this weird word called confounding, which if you try to ask somebody to define it, it confounds them. All right, so we can do these 3 tasks, but then we can do these tasks in the service of the science of medicine, the practice of medicine, or the business of medicine. On a medical campus or in a university, usually we tend to glorify the science. We get excited about changing practice and pretend that if we change practice, healthcare will change. The 2 outcomes, mortality and cost, will change. Not true. I'll give you a concrete example. There's some nice work at Northwestern, actually, by Nigam Shah, no relation to me, where they analyzed people with a disease called heart failure with preserved ejection fraction. I love to make fun of that disease because you ask a clinician, what's heart failure? They say, your heart's not pumping enough. What's the meaning of preserved ejection fraction? It is pumping enough. So like, wait a second. So heart failure with preserved ejection fraction means you have a disease where your heart is not pumping enough, but is pumping enough? But it is a thing people get. And by doing some analysis of multiple kinds of data, gene expression, lab test results, and so on, they figured out that that disease is heterogeneous and has 3 subtypes. Subtype 1, you're fine for a decade. Subtype 3, you drop dead in 2 years. It's a massive advance in the science of that disease. Now we know that it's something different. Like, it's not one disease. You know, diabetes was one disease before it became type 1 and type 2. That happens in medicine all the time. Practice advances if I get 2 more things. Patient walks in and I have a test. Could be an algorithm, doesn't matter. Could be a regression, could be a deep neural net, could be something running on the echocardiogram video. I really don't care. I want to spend $1 and say, are you subtype 1, 2, and 3? Or 1, 2, or 3? And after that, we also need a treatment. That if you're subtype 3, I need to be able to do something more for you that I would not do for subtype 1. Or if you're subtype 1 and you're going to be fine for a decade, I don't do anything, just send you home. So that requires a change in policy. So here you need the test, you need the treatment, and then we do those things for 5 years to 10,000 people, and they live longer and cost less, or both. That's when we have changed healthcare. So it's a long road from here to here to here. And the drop-off rates are probably 1 in 100, 1 in 50. I don't really know the exact number. This is perhaps the most important part of our conversation. For students in the audience, anytime you jump on a project, try to force it into one of these 9 cells. It'll save you a lot of agony later. I often meet with what I called engineering refugees, who in their first and second year sort of started on a project in the science of medicine and were led to believe that if they succeed, they will change healthcare tomorrow. And then they're smart people, so by the 4th year, they figure out that, no, something's not right with this statement. And they say, can I work on something that actually changes patient lives, like tomorrow? Nothing wrong with advancing the science, okay? If science did not advance, none of this stuff would happen. But you have to be honest about what you're trying to accomplish. Science advances, you go publish in Nature Science Cell. Practice advances, you go publish in JAMA Lancet New England Journal. Delivery advances, you don't publish. The CFO gives you an award, maybe you start a company. Okay, so let's look at a couple of examples. So this one is one of the harder ones, where we're making recommendations for practice. And for some of you have probably been subjected to the agony of doing an observational study, where you have a question, patients with diabetes who don't respond to metformin. What is a good second-line drug after metformin? And then you end up having a conversation with somebody, they compile a data set, they give you the data set, you then decide how are you going to define your exposures and the outcomes, and you do propensity matching and argue about what's the right inference mechanism. It takes 6 to 9 months, and then you write a paper, and then there's more review time. It takes about a year. Let's say 9 months. We launched a service in 2018 that on demand, at the bedside, if a doctor has a question, we will answer that in 2 days. And we did 100 cases. That's 137-fold speed up from 9 months. And the reason this matters is that everybody knows there's evidence gaps. I mean, 80–90% of the time a physician in a specific situation is guessing. I can cite paper after paper proving that. My favorite one, the title is Deciding Without Data, where people followed how many decisions they're making in any given week, and they found that only 3% of those decisions had any study to back it up. 3%. So there's a lot of CS that happen here, okay? Handling timelines, Allen interval algebra as opposed to relational algebra, handling knowledge graphs, cohort building, doing high-dimensional propensity score matching, automated testing, did your matching work or not? But none of the clinicians give a damn about that. They do not care. They just need to know, I have a kid with mononeuritis multiplex, we're going to do spinal taps and this and that. What do you recommend? I say, well, past 180 kids that had this, when we gave steroids, they were fine. So maybe you want to consider that. And then it's their decision and say, all right, we're not going to do all of these invasive procedures. Kid goes home 4 days later. So when we finished this, our dean and CEO said, well, this is awesome. How are we going to scale this? And I was like, well, you fund my 2 students and a staff member for perpetuity, and then we'll run it for Stanford, whatever, as a clinic. We actually call this the informatics consultation service, just like a psychiatry consult or radiology consult or what have you. They said, no, that's not what we mean. How are you going to scale this nationally? I was like, damn, I'm not going to do that with my 2 students. So we spun out a company called Atropos Health. And here, I like showing this because the project was called the Green Button. They actually still call it that. I tried to convince them they should call it the Green Button Company, but they would not have any of that. Stanford is a user. We did about 1,000 consultations just as one institution in the past year. And there's an animation. Yeah, there we go. Basically, you get publication-grade evidence every time you ask a question. And I say publication-grade because some of my friends took this report, wrote an intro and a discussion, submitted it, got it into JAMA. The inference could go either way. But JAMA head and neck surgery, okay, not the main JAMA. All right, let's look at another example. This one is about prediction. Prediction is hard. I like sticking with classification. Because when you classify, you don't change the world. When you predict, you introduce issues that could change the world, that could change the data underneath you. You're kind of interfering with the world when you make a prediction. Classification is easy, it's safe. But we're going to look at prediction. So here, what's going on is we're going to make a prediction about who's going to die in the next 1 year. And based on that, we will do something called advanced care planning conversations with those patients. And this is the key thing. It took 7 years from idea to value, which is on this slide. I'll first walk you through the slide. So here's time. Here's the number of unique patients that got advanced care planning. And you can see that the gray line, which is doctors, goes up and then is flat. And then this red line is continued to going up, and they diverge quite a bit now. Because if we make predictions that always require a doctor to do something more, last time I checked, we had a physician shortage. And now we're asking those exact same people to do more. Well, how's that going to work? So this phase is where we messed with the intervention, which in this case is advanced care planning, used to require a palliative care doctor. And Dr. Vinnie Tutberg sort of came up with a regimen to train the respiratory therapist, the physical therapist, the spiritual care worker, the med student, the resident, the fellows. So anybody who sees the prediction can start having that conversation. So we built a model like 2015, 16 timeframe. This is when we believe we hit success, in the sense that the intervention can now be done sustainably. Now in this case, it's a relatively easy intervention. We're not injecting anything into the patient. It's more about, how do you wish to pass? What are your hopes and dreams? What would you want your final days to feel like? It's an awkward conversation to have. But when you have it, there's RCT-based evidence that people live longer, cost less, and have a better quality of life. It's probably the most important thing you can do in a complex care environment. It is a quality metric that every hospital cares about. I tried working with multiple technology companies on this, and not one of them wanted to touch machine learning and mortality in one sentence. Not one of them. Okay, but this is alive and well running. The key point is 7 years. Okay. So models stratify by risk. Value comes from the responsive action. If you make predictions and don't do anything, nothing happens. So we saw this example, predict mortality, improve advanced care planning. Here's a bunch of other examples. These are all science examples. These are more of a practice example. The one I showed you is on the borderline. You could call it clinical, or medical, you could call it healthcare. Some of these are amazing. Like there's work from UC Davis, which serves a bunch of Central California counties. They have a model running that if in a hospital in Fresno, for example, someone has a stroke, they can classify hemorrhagic versus ischemic. And if it's hemorrhagic, they can put the person on a helicopter and take them up to Davis and drill a hole and get the blood out. Now the model's awesome, but it's no good until you have the helicopter. And we don't have infinite helicopters. So there's a hard capacity constraint, which sort of leads to this amazing graphic that we have to study this interplay amongst models or work capacity and policy as to, when are we going to put somebody on the helicopter? How many helicopters do we have? And the cost benefit of the action. I would submit that we spend way too much time on this. Way too much time, and not enough here. So I'm going to show you one plot just to hit home this point. What we're looking at on screen here is, I don't remember which model it is. Let's say mortality. We're making a bunch of predictions, or let's say it's hemorrhagic stroke versus ischemic stroke. I'm just going to rank order the cases by the predicted probability, or 1 minus the predicted probability. We take action on the first one, we get some benefit, some utility. Hours saved, dollars saved, happier patient, happier doctor. Doesn't matter what the units are. And we keep taking action, second, third, fourth, fifth. At some point we hit max utility, and then we see diminishing returns. You should be able to answer on day one, if you had a prediction and you have a workflow, given your capacity constraints, how far down the list are you going to get? Because if you can only go this much and your max utility is here, that's not good. And if your max utility is here and you're walking all the way down the list, that's not good either. You're just wasting time. If you want to do these analysis, here's the GitHub repo. Peer-reviewed, all of that. There's a paper as well. But I guess most people here would care more about Python than PDFs. Just to give a sense of how bad the state of affairs is, this is I won't name the people. She's a collaborator, impeccable science, creating a model with 4 variables to identify who should get an immediate 12-lead EKG when they show up in the ED. Okay? Validated at 4 sites, mostly NIH funded. Impeccable science, okay? Generalizability, prospective validation, cost them 10 years and $28 million. There's 121 or 23 residency fellowship specialties in medicine. And if every resident or fellow wants to build one model at one of our clinics, that would be $35 billion. We're going to bankrupt healthcare because of our current ways of organizing work are just unsustainable. And all of this is before language models came around. Okay? All right, so let's spend about 5 more minutes. We'll zoom through the language model business. So here, I didn't want to recycle the star, so I came up with a different graphic. It still has 3 points. I think we need to focus on this part, defining and verifying benefits. There's a lot of buzz around building models, billions of parameters, this many $1 million to do the computation, yada, yada, yada. So let's just dive in with examples. So remember, the patient timeline has a language. Why are we still training language models with natural language, English, Spanish, German kind of language? We can look at this order of tokens. It's a language. The medical record is a series of medical events. So we should just have a sequence of medical events and try to learn the grammar around that. Some of you know Matthew McDermott, who's right there. I'll just say this. I'll write it, I won't say it, so you have to read it. And then I want you to go ask him about it. All right, so patient timeline has a language. So that gives us 2 ways to build language models. We can keep working with documents and then do chat and summarization, or we can look at timelines. My team likes to build these kinds of models, and we call them foundation models for electronic medical records, or femurs. Femur is kind of the longest and the strongest bone in your body, so that's a little bit of a tongue-in-cheek. But these then allow you to forecast what's going to happen. They allow you to create embeddings on which you can train classifiers. They don't talk to you, unfortunately, so there's no flashy demo you can do. But if you do these timeline-trained language models, and then you build your classifiers or your predictors, so Climber is for classifiers, Motor is for predictions, you basically get increased classification accuracy. Classifiers decay less as time passes. They port better across subgroups and sites. Trains faster, needs less training data. All of these little numbers up there these are papers. Lillian Sung's group here at Sick Kids has been a close collaborator on this. Stephen Fole, one of my former students and now a scientist at Google, is here. They can tell you all about how we did these studies. Lawrence is here. I don't see Lawrence from Lillian Sung's group at Sick Kids. Yeah, so talk to them. The point being, if we do these embedding models, what awaits you? How can it help get a handle on reducing the agony of building them, maintaining them, and sharing them across sites? And then don't just take my word for it with this pretty plot that shows Climber, this blue plot, being better than everything else. We're also releasing the data sets that you can verify it yourself. So the Earshot data set, about 6,700 patients, 15 labels, and you can make this plot yourself to convince yourself that these event stream models are worth it. And if you like multimodal, you want pictures, a couple of modalities of pictures, structured data, and some documents. This is the data set, 3 modalities, about 19,000 patients. And you can verify the performance of motor, which is going to forecast something into the future. All right, so that's our stuff, but what is the rest of the world doing? So we did a review. Most people don't give a damn about these femurs and timeline-trained models. They're still working with language models in the traditional sense, the GPT and its brothers. So this is a review, 519 papers, where we asked 5 questions. What is the data being used to do the evaluation? What is the healthcare task being done? What is the language task being done? How are you evaluating? So what's your metric and which medical specialty, okay? I'm only showing you 3 on screen here. Evaluations in 95% of the studies were done not using EHR data. Okay. Healthcare task, the majority of them are doing things which are essentially enhancing or evaluating your medical knowledge. The language task, question answering. Taken together, this means we're basically doing USMLE exams, which yesterday Sheikh talked about how we're saturating that kind of evaluation. We're enamored with accuracy. We're not looking at deployment metrics or calibration and uncertainty. Because health systems don't have infinite money. They're usually working on a 1% profit margin. And you can't expect to sort of raise $1 billion and then make it up from charging health systems more for their health IT. That is not going to reduce the cost of healthcare. And so you got to be really thoughtful about what are you pitching and what is it going to cost us in terms of time, money, energy, and agony to run something. If I can build a readmissions predictor using 15 variable regression, why would I do few-shot prompting on a large language model and pay you $5 every time to get the same probability? Like, it makes no sense. All right, so then this is what people are doing. So we said, all right, if we try to verify benefits of these off-the-shelf LLMs, verify benefits as in things that we really want to do. I told you about that green button project. So we took those questions and fed them to GPT 3.5 and 4. So about a year old now, so it's kind of irrelevant in today's timeline. From 3.5 to 4, agreement. So agreement, in this case, we had the reference answer. So we submitted the question to the language model, get the answer, show it to 12 doctors, and ask them to adjudicate, saying, is the new answer agreeing with the answer we had? Is it disagreeing, or you can't tell? So agreement going up, disagreement going down, cannot tell going down, life is good. But about half the time, the 12 doctors had no majority how to interpret the response being given to them. This is otherwise known as having a second-year med student. If half the time it says something that you can't decide whether to trust it or not, that's not going to help you at the bedside. And then everybody talks about summarization. Summarization was, I think, right here. And in the popular media, without evaluation, people are talking that, oh, we're going to use language models to summarize medical records. I like verifying stuff. So we said, all right, 15 docs, tell us what you're going to do. So some of them said, summarize from the EHR strokes that the patient had and their neurological deficits. We give the EHR, language model produces a response. We have the right response from the physician. Even in the best case, multi-retrieval, all of that fancy business, 35% error rate. 35%. So that data set is here, not released yet, but it will be out very soon. And then you might have heard about all of these things about looking at using language models for responding to in-basket messages. A lot of press around that. Very few papers around that, 2 from Stanford, 1 from UC San Diego. Stanford paper shows no time savings, 0 time savings. UC San Diego paper shows 22% increase in time spent because now you have to read the draft and then edit it and then maybe delete it and rewrite it yourself. But doctors feel better, happier. Cognitively, they feel less burdened. So definite value there. Not what we expected, though. There's no efficiency gain. There's no productivity gain. Now you have a happier doctor. And you can build a business case around it, less burnout, less turnover, and so yes, it's worth paying for, but it's not going to revolutionize healthcare. And it is not going to lead to increased access because no one's going to see more patients between 8 and 9 p.m., which was the time they were doing this in-basket work anyway. So we got to be really thoughtful about how we verify benefits. All right, so I'll close out with this last slide. Several people here are researchers, PhD, postdocs, fellows. These are what I think are the fruitful areas of research. Study this interplay amongst models, capacity, and actions. Derek talked about how when models make predictions, we're changing the underlying data distribution. What could that lead to? How are we going to survive in that scenario? There's a lot of good theoretical work to be done there. If you do that work, please release a software package that he and I can use instead of having to read your PDF and try to figure out what you did. You really have to think about deployment. Take the time to understand health IT. Stanford runs 1,255 software systems. The EMR is one of them. Mimic is not the start and end of EMRs. Like, I have a very love-hate relationship with Mimic. I love it because it's open source. So many people can use it. But at the same time, like, it gives you this sense that that's it. Device evaluations that respect the different priorities of medicine and healthcare. If you're doing medicine, do medicine. If you're doing healthcare, do healthcare, but design the evaluation so that it meets the needs for healthcare. Don't do a medical evaluation and claim victory in healthcare. And then balancing technical innovation, building bigger, better, larger models, with verifying the presumed accuracy, presumed value proposition. We might have a trillion parameter model. That's great. But is it going to lead to efficiency or productivity gain? And if neither of them, then why are we talking about it in healthcare? All right, so I'll leave you with that. I already acknowledged the people in my team and everybody, so we're ready to go into questions, and thank you.